So far, we've been looking at the paths of individual particles traveling along a curve or a line or something. What we could do is we could have two particles moving curves in. It could be 2 or indeed 3 dimensions. And in that case, there are quite a few questions that they could ask us about those two particles. A really common one is, are those two particles going to collide? Now, in order for them to collide, two things have to happen. They have to have the same coordinates, but not just the same coordinates, they need to have them at the same time. So same coordinates at same time means that the particles are going to collide. Instead, if they have the same coordinates but at different times, this is when the particles cross. So in that case, they have the same coordinates again, but instead of happening at the same time, it's going to happen at different times. So they're two really common questions. Do the particles collide or do they cross paths? Other things that we could be asked are about distances. We could be asked for an individual particle's distance from the origin, and that's just the magnitude of RT, because remember, that vector R is a vector pointing from the origin to our point for different times t. So just finding the magnitude of that vector gives us the distance from the origin. Not too bad at all. If we're looking at the distance between particles at a particular time, we're going to have to, apologies, that should not be subscript, we need to subtract one of those vectors from the other and find the magnitude. It doesn't matter which one you subtract from which. Now, interesting, why is that so? So let's say we've got a vector, sorry, I can't help myself but label these. So we've got one vector, which would be R1 of t, and we've got another vector, R2 of t. Now, what we're going to do is we're going to subtract one away from the other. So let's do R1 minus R2. So let's get R2 and flip it. So that will be the negative vector. So when we do R1 minus R2, that's R1 plus negative R2. So the resultant vector is going to be this one here. Now, how does that relate to the distance between the particles? Good question. You'll notice that when you subtract one of those vectors from the other, it's equivalent to a vector pointing from the endpoint of R2 to R1. Now, if instead you had done R2 minus R1, you would have just had a vector in the opposite direction here, pointing from R1 to R2. The direction of that vector doesn't matter because, as I said, all we care about is finding that magnitude. So that's why subtracting one vector from another and finding the magnitude gives us the distance between the particles. We have a position vector of a particle. We're told t is greater than or equal to 0, and the position vector is given by this. We want to find the position of the particle at t equals 9. Well, that's not too bad. We're just going to substitute t equals 9 into this. So 6i minus 3j. Nice and simple to get started. Now, if we're asked to find the distance from the origin at t equals 9, that means we're finding the magnitude of the position vector when t equals 9 specifically. So that's just going to be squaring the I component, squaring the j component. That's technically negative 3 squared. So that's going to give us root 45, which will be 3 root 5 units, because it's a length. Okay, that one was really quick. I thought we had more to it. So that was a single particle. We've now got a question with two particles. So we've got these vector functions or position vectors for any time t. We've got r of t, and we've got R1 of t, and R2 of t. And we're again told that t is greater than or equal to 0. Cool. So we want to find the point at which the particles collide. Now remember, to collide there are two conditions that must be met. They have to have the same coords, and it must be at the same time. And keeping in mind that time needs to be greater than or equal to 0. In order to find the time t at which the particles collide, we need to equate the I components of each vector and the j components of each vector. So in that case, we're going to have 2t minus 3 equals t plus 2. And that tells us that t, if we subtract t, add t is going to be 5 seconds. So that was when we equated those I components. Equating the j components, we're going to have t squared plus 10 equals 7t. So t squared minus 7t plus 10. If we factorize that, equals 0. Now that gave us two solutions, t equals 5 and t equals 2. And you might be tempted to think, oh, we found another solution, t equals 2. That's only true for the j component. Because it's not also true for the x component, we need to actually reject this solution. So we're not rejecting it because of any restrictions upon t, we're rejecting it because we don't have the same value of t for those x components, so that can't be one of our solutions. It needs to work for all components that are involved. So now from this, we know that the particles collide at t equals 5 seconds. So now what we can do is we can substitute in that value of t into either of the parametric equations that we have. I reckon I'm going to sub it into R2 because that's simpler. So if we sub it into R2, and we're subbing in t equals 5, that's going to give us 5 plus 7i plus 7 times 5j. Oops, sorry, I was getting ahead of myself. 5 plus 2. So 7i plus 35j. So that gives us the vector pointing to that point, but this question is asking for the point at which the particles collide. And that point just corresponds to the endpoint of that vector, so therefore the coordinate is 7, 35. You could have also gotten that if you'd substituted in t equals 5 into that first equation. Doesn't matter which one you choose, because obviously they're both going to point to the same point. So in order to find that time t, we equated components and we found this. You've got to make sure that time works for all components, if indeed they do collide. If the question says check whether the particles collide, you might have a situation where you have a solution that works for one dimension that doesn't work for another. So check that. Once we found that time, we then substituted that into either of those vector equations to find that coordinate. Now, we've got the points at which the two paths cross. Now, take care. The conditions for this are that we're going to have the same coordinates, but we're going to have different time. So what that means we're going to do, we're going to rewrite R1 here. Now, because the times are different, I am going to use a different parameter to represent R2. So instead of t, we're going to call it something else. S I'm going to use. You could decide on something you prefer. And we've got 7sj. So we've got different parameters here because the time is going to be different. So in the first one, we use the same parameter t because we were looking for a time that was the same, so we could equate those parameters, no problem. But in this one, you need to manually change one of the parameters. You could have used t1 and t2 if you preferred. I've just changed it to s so I don't have any confusion. Now it starts off pretty similarly. We're going to equate those I components, so that says 2t minus 3 has got to equal s plus 2. And if we equate those j components, t squared plus 10 is going to equal 7s. So we've now got a set of simultaneous equations here. Now, if we substitute that first one, let's rearrange that. S is going to be 2t minus 5, and we'll sub into 2. That will give us t squared plus 10 equals 7. And then instead of s, we'll have 2t minus 5. Let's rearrange that. T squared minus 14t, and multiply that, you get 35 plus 10 plus 45 equals 0. So that gives us two possibilities, t minus 9, t minus 5 equals 0. So that gives t equals 9, t equals 5. So notice that t equals 5 is the one that we had before. So when t equals 5, the point that corresponded to that was 7:35. So this is where they collided. If we look at the t equals 9, and we substitute that into one of them, let's do it into R1 because we're looking at t, so we have to substitute it into that. Because we didn't find the value of s. We eliminated s, and we're substituting into that. So t of 9 is going to be 2 times 9 minus 3, I plus 9 squared plus 10j. So that gives us... Sorry, I don't know why I'm working in green still. So that means the coordinate is 1591, because remember, this vector points to that point, and that's where they crossed paths at different times. So if we substituted in this point into R2, we would find the value of S would be something different. Now, let's look at the last question. It says the distance between the particles when t equals 1. Okay, so we're using a common value of the parameter there. So we're going to go back to having R1, and we're substituting in t equals 1. And substituting that, we get negative I plus 11j. Double check my algebra there. R2, when t is 1, we're going to have 3i plus 7j. So, to find the distance, we take one vector away from the other. Doesn't matter which, because all we care about is the magnitude of that vector, not its direction. So that's going to give us, if we're doing R1 minus R2, we're going to have negative I minus 3i, so minus 4i. And then we're going to have, doing R1 minus R2, 11 minus 7, so that's going to be plus 4j. So magnitude of that is 4 squared plus 4 squared, which is going to be 1632. So that's 2 lots of 16, so 4 root 2 units. Fab, not too hard. So let's apply this to an exam question. A little more involved, we've got some trig in there, but nothing we can't handle. We've got a position vector from an origin O of a model helicopter t seconds after leaving the ground is given by this long equation here. We've got 50 plus 25 cos and then pi t over 30 inside of that cosine I, and then we've got something similar looking except for the sign for the j, and we've got a 2t over 5 for the k. Now it says I is the unit vector to the east, j is the unit vector to the north, and k is a unit vector vertically up. Okay, that's good to remember. Displacement components are measured in meters. Good. Find the time in seconds required for the helicopter to gain an altitude of 60 meters. So altitude is a word that you need to be aware of, and that's the distance above the ground. And the only component that has anything to do with the distance above the ground is the k component, because it says the k is a unit vector vertically up. So if we want to find the time in seconds required for the helicopter to gain an altitude of 60 meters, that's going to mean that the k vector component, 2t over 5, has to equal 60. So that means we're going to have t is 150 seconds multiplied by 5 divided by 2. Okay, 1 mark, so we just need the answer. Okay. It says find the angle of elevation from O. So if it's an angle of elevation, that's going to be an angle from the horizontal looking up at the helicopter when it's an altitude of 60 meters. So if it's 60, this distance here is going to be 60. Give your answer in degrees, correct to the nearest degree. In order to do that, unfortunately, we only have one side length at the moment. We don't have the hypotenuse and we don't have that adjacent side. But we could find this distance along the ground, because remember, it says I is a unit vector to the east and j is a unit vector to the north. So if you look at the I and the j components, we could find the distance travelled along the ground. Now, they've again said altitude of 60 meters. So that means time when the altitude was 60 meters was 150 seconds. We only had one possibility of what that could be. So to find that distance along the ground, let's just look at, well, let's know what we're doing. Distance along ground. That's just going to be the magnitude of the I and j components of this vector when t was 150 seconds. So that means we're going to have, for that I component, we're going to have 50 plus 25 cos, and inside of that, t is going to be 150 times pi over 30. And that's going to be I, plus, we've got the 50 plus 25 sine, and we said t was 150 times pi over 30 in brackets j, not I. Okay, so finding the magnitude of that, let's get our CAS. Okay, sorry, I didn't have that in standard form. So we get that length is 25 root 5 units. So that's the distance along the ground. Now that we have that, we can use some basic trig. Let's use tan opposite over adjacent. And remember, we want that theta in degrees. Okay, they ask us for the nearest degree, so that's going to be 47 degrees. Okay, this last question says, after how many seconds will the helicopter first be directly above the point of takeoff? If we go back and look at this, we can see that this portion, the I and J components, are describing motion in a circle that is not centered at the origin. So this K component just increases the height, and if we were looking from a top-down view, we would see it going in a circle, but it's going to be spiraling upwards. So the time it's directly above the point where it took off is going to depend on the period of the sine and the cosine. So to find that period, we've got 2 pi over that pi over 30, the coefficient of that t, which is 60 seconds. Great. So I encourage you to have a go at these questions and have a look in the assessor's report to see how you went.